Okay. Okay. So can I go?
We start the second part of our Gong show, and the next speaker will be Carlos Bercini from ICTP, who will tell us about the Wilson loop and their relation to large spin correlators.
Yeah. So yeah, thanks a lot for the opportunity to talk here. So the plan for today's talk, it's very short. So I want to define the correlation function that I will be talking about. Then I will comment about its relation with the Wilson loop. We will sketch a little bit this derivation through some bootstrap, and then we're going to tie the results, the future direction with integrability. So basically, what I want you to say it's the following. So we want you to consider 6-point functions of the lightest scalars of some some conformal gauge theory, sorry, in the planar limit. For example, in n equals 4 superring Mills, this will be correlation functions of the 20 prime operators, trace of phi squared. These 6-point functions, they have 9 cross ratios, 9 variables. 6 of them we call v's, and 3 of them we call u's. So for example, here I presented v1, so it's this blue distance divided by the pink ones. And all the other v's are just cyclic rotations of this image here. And here I presented u1, again, the blue distance divided by the pink, and all of the other u's are just rotations of this picture. We are going to study these correlation functions in a very particular limit called the double light cone limit. And in this limit, we're going to make all this distance to be null. So xi plus 1 goes to 0. This means that all these v's that I just defined, they are going to 0 in these limits, while the u's, they remain finite. And that's also motivates why we are looking at 6-point functions, because if we look at 4 or like no squares and no pentagons, they do not have finite cross ratios. So in this sense, the 6-point function is the first non-trivial case. That's why you're studying it. Okay, so what we're studying this limit is that because in this limit, in this double light cone limit, we expect some relation with Wilson loops. And the interpretation as worked out here in this paper, it's straightforward. It's as follows. Once we make some distance to be null, we have a divergence. Sorry. Like even in free theory, it's 1 over x squared to the propagator, it diverges. And this divergence can be interpreted as some very fast particle propagating between these two operators here. This particle interacts with the background gauge field, and that's basically the effective definition of the Wilson line. So once we make the whole parameter to be null, we have a Wilson loop. More precisely, the duality is as follows. So the 6-point function and this double light cone limit, it's equal to the Wilson loop, but the Wilson loop also has divergence. Luckily, it's easy to factorize this divergence associated to the cusps in a factor that we call Sudakov. And what's left of the Wilson loop is the renormalized Wilson loop, which is a finite quantity that depends on the finite cross ratios U1, U2, and U3. And this relation is a little bit subtle because these lines, they interact with one another. So effectively, they pull each other in some sort of back reaction. So you have this recoil factor that accounts for that. So now let's just study a little bit more this correlation function in the double light cone limit. So what happens in the double light cone limit is this following. So let's work out all this very dense slide. Is the following. The first thing we do is we call snowflake OPE. So we consider the operators 1 and 2, they make some OPE. 3 and 4, they have another OPE, and 5 and 6, they have another OPE. All these operators that are flowing these OPE channels, they meet in the very center. And in the center, we have a 3-point function of 3 spinning operators. This 3-point function has, again, like some structure constant and has a lot of sums over, and has the sum, which just is the sum over invariant tensor structures, right? It's the spinning, so we need to sum over all the invariant spinning tensor structures. And for each one of them is parameterized by this little L here. So just to be a little bit more precise, the 6-point function can be written like this. So we have a sum over all the dimensions and spin of the operators that are flowing here in the middle. And then we have the 3-point function, which contains another sum over tensor structures, and then the structure constant of 3 spinning operators. Everything weighted by an object that is fixed by conformal symmetry that I call the conformal block. Once we take the double light-cone limit, several simplifications occur. So let me just briefly sketch through it so we can get to the end. But the first thing we do is that we make all this pink distance to be null. And that projects into leading twists. So now all the sums are projecting twist 2 operators. Then we make the blue distance null. And when we make this blue distance null, all the sums are projected into large spin and large polarization sums. And finally, one of these sums, namely the one in over this polarization's little l, they can be done by saddle point. So in the end, what we have our 6-point function. It's equal to leading twist and large spin. And here we have the structure constant of large spin operators, weighted by a very, very simplified conformal block, since 6 of its 9 variables were sent to 0 in this limit. But that's not the end. We get the 6-point function. And we choose, in order to get the 6-point function, we choose a particular channel. So we choose 1, 2, 3, 4, and 5, 6. So you choose this channel, but the 6-point function doesn't care which channel you choose. So the answer in the end should be the same. Doesn't matter the channel. And that's what we call cyclists. And it turns out that for arbitrary structure constants here, this function is not cyclic symmetric. And imposing that this function, this 6-point function, is cyclic, it constrains the structure constant. It constrains the structure constant up to a function that is cyclic symmetric in the big U's. And this function that is cyclically symmetric in the big U's is precisely the renormalized Wilson loop. In other words, we get that the 6-point function, it's the renormalized Wilson loop times some Sudakov factor times some recoil. But most importantly, by looking at the 6-point function in the very core of the 6-point function, as I advertised early, we have the 3-point function and the structure constant of 3 spinning operators. And it's precisely this, as was conjectured in this paper, it's precisely this 3-point function, this structure constant of 3 spinning operators, that in the limit of large spin gets mapped to the renormalized Wilson loop. And the precise map is here. Where these little L's here, they are just replaced, they should be understood, I just replaced them by the saddle point value. So what this means is that on the left-hand side, we have the 3-point function that depends on spins. And on the right-hand side, we have the renormalized Wilson loop, which depend on the cross ratios UI. Okay, so let me just conclude and look this map through the integrability sense, and then we are done. So that's basically plans for the future / comment about integrability. So the first thing I want to do is like split this picture in half and comment about them separately. So we know that the structure constant can be, it's a pair of pants that can be broken down into 2 hexagons. And then we are structured to sum over these BMN excitations. On the other hand, the Wilson loop, it can be broken down by concatenating 2 hexagons. And then we sum over these GKP excitations here. But now we work out precisely the relation between the structure constants and the Wilson loop. And then we can ask ourselves, what does this mean for integrability? So the plan now is to understand how this, since we have large spin, how this huge sum over BMN excitations should transmute to some GKP excitations, or how these hexagons are related to pentagons, how these closed string descriptions are related to these open strings descriptions, and so on. And perhaps by understanding better this arrow, we can maybe find a more unifying or understand a more unifying integrability description in N equals 4 supernomials. So yeah, that's basically it. Thanks a lot.
Yeah, thank you, Carlos. That's thanks, our speaker. Okay, and now we have time for questions.
So I could ask, so this states and 3-point function are already kind of a JKP strings, right?
Sorry,
because highly, the states and 3-point function are already kind of JKP strings, right? It's highly spinning ones.
Yeah, and they have huge spin, right? Like infinite amount of spin.
And then the right-hand side is also JKP essentially.
Yeah, but yeah, but when you do the hexagons, you start with BMN, and then you have to sum over like an infinite number of BMN excitations, and we don't know how to write this in the GKP vacuum, right? But that will be a very good thing to do in the hexagons. If you could make the vacuum of the hexagons GKP and understand how to do that, then for sure this arrow will be much more simpler to understand.
Right. So the problem is that hexagon part, because you need to start from BMN and
yeah, and then you have to understand
and
how to
once
make
you
it.
get the limit, then the map to pop should be kind of transparent.
Yeah, I agree.
Could I ask a question?
Sure.
Is it right to think that in this limit you do not feel the finite size corrections for the Wilson loop side, since you are in GKP and large spin and so on? I mean wrapping type of corrections, which are not present in the pentagons.
Well, large spin is a recipe to suppress wrappings.
Yeah, I just wanted to confirm.
Yeah, I believe so. Yeah, I would claim, yeah, it's just the asymptotics of these guys that should reproduce here.
Thanks.
So technically, is it possible to go to the next corrections around the saddle point, and is there something interesting about it?
But then you should relax light cone, right? You should go away from light cone. Could be. Then you break the duality with.
Well, and my second question actually was about. Oh, okay. Let's first. Do you have?
Yeah, I don't have anything after like relaxing that. I don't know. Yeah.
So also, as far as I remember, the duality between like separated operators and Wilson loops is related to dual conformal symmetry, right? So is there some, do you see, can you say about it something in your context?
Yeah, from the correlation function point of view. Yeah, because like the only thing, I think like the only thing that we can claim, like we get in the end that everything is fixed up to some function that is cyclic symmetric in the use, and this function turns out to be the Wilson loop. So in any cos for super, okay. So, but then like what you're asking is something that I think that is like a property of the Wilson loop itself. And I think from the bootstrap point of view, you cannot achieve, like you cannot peek inside what's inside the Wilson loop. So you can find like you get this function, but then you cannot like peek inside using the bootstrap and see that it has all these rich properties that you're asking for. But we can ask something like, knowing that, like, suppose that I know this and then I know the both sides, then I don't know. Yeah, if I know both sides, then I could in this duality, perhaps I could say something smart here, but like stopping here on the bootstrap, and I don't see how could I say something more intelligent about the Wilson loop. Like,
Thanks. Any other questions?
So in terms of highly exciting hexagon, how hard is it going to be, because the complexity naively increases super rapidly.
Yeah. If you just blindly try to do it in the computer, it doesn't work. So you need to be smart, and that's where we're working now. And I don't have anything clever to say, like of making this like huge BMN now. Like we don't. We have small, like we work out this for a small spinning operator, so we can just like spin 6, 4, and 2. We can reproduce these guys here, but like from going to infinity, it's a long way.
And by the way, very technical thing, just to precise. So about the kinematics, everything was collapsed just to one structure, yes, standard structure in the end. So did you have okay? You have this kinematics of like separated points, but is there something else? I mean, other coordinates to fix it in some plane or something like this? Do you assume some extra?
No, the only thing that we assume is it's we don't fix anything more than just saying that these guys are going to.
Yeah, just is good. Okay,
Yeah.
okay, good. Mhm. Okay, so probably
Very nice. So next, stop recording.
yeah.